So on question 016, question 016, today's the 21st, right? Is the question where I want you to find the greatest lower bound and the least upper bound. And the greatest lower bound and least upper bound need to be powers of 2. So what happened is the following, is that I give you that function f, which tells you your stopping condition, essentially. It's how you detect when you're supposed to stop. So I gave you a function that tells you if you're supposed to stop because I didn't want to give you the number that I was hiding. It was like I hid the number in a box, so I didn't want to give you 73. I just wanted to give you a function that would respond to your guess. So when I first wrote that exercise, the function, the stopping condition function, was the following. Was a function that did the following. So I hide n, which is to say my function knows n, and then I give you a function f, which gives you the following. It gives you a 0 if m is less or equal to n, and it gives you a 1 if m is greater than n. So this was the original version of the stopping condition.
What was the name of this function?
Well, I think I called it an oracle.
Okay, make oracle.
Well, the make oracle function makes this function.
Okay.
So this was the original one. Okay, and I wrote the key and got it all prepared, and the exercise was only computing least upper bounds. And then I said, you know what? I think it'd be good if they also computed the greatest lower bound. So then I added to the exercise and made it to where you needed to compute the greatest lower bound, and it became expedient for me to change the stopping condition. So then I changed the stopping condition to the following. So again, I hide an n, and now the stopping condition is -1 if your guess is too small, 0 if your guess is right, and 1 if your guess is too big. So the stopping condition changed from this to this, and the problem is that, I mean, you can even see that this function has 2 clauses and this one 3. This function gives you just slightly more information. Just slightly more information. And in the test case, I'm counting the number of guesses that you make. And if you don't make the right number of guesses, then I assume that your program is not correct. Now the problem is that my test function was using the right number of guesses for this stopping condition, not for that one. And the distinction is that in the case that the number that I hide happens to be a power of 2, if it is a power of 2, then you can actually use one less guess. So what was happening is that most of the time it looked right, and then every once in a while, due to randomness and other things, it might be wrong. And so your function could still be correct, and then the test case was wrong. So that's interesting. It's an interesting exercise. So what we're going to do is I'm going to make another exercise. What I did is I made it to where your function, if you were within 1 of the correct number of guesses, then you're right. So now we'll make one more version of the exercise where you must get exactly the right number of guesses, and I'll carefully code it to count correctly. Okay, so this was for homework 016. But this kind of thing happens all the time, which is why you have software tools like GitHub where people can, submit code and then it's not working right, it's not passing the test. Most of the time that means that whatever you submitted is not right. But on occasion it actually does mean that the test is not right. Okay, so interesting. That's also why none of these homework assignments have fixed due dates except the end of the semester. Because little things like this can happen. Okay, any questions before we get to new things? Okay. So, today we're going to still talk about division. So as a reminder, given A greater or equal to 0 and B greater than 0 and A and B are in the integers. So A is a non-negative integer and B is a positive integer. We've already said a number of times that there exists unique Q and R in the integers such that A is B times Q plus R. And we can make a very stringent requirement on R. What is the very stringent requirement on R?
R is
Less than B, and greater or equal to 0. Less than or equal to B, no. 0 is less or equal to R is less than B. Okay, so let's make sure everyone knows the names of all of these. So I think everyone will know this one. This one is quotient. This one remainder. Essentially everyone knows those. The names of the other two, it's hit or miss whether or not you know those. So what is the name of B? Yeah? Divisor. Divisor. And what is the name of A?
Dividend.
Dividend. Okay. So we've talked about this, and we have at this point implemented two different algorithms for computing Q and R. We did the repeated subtraction where you just repeatedly take away B until you can do so no more. And then we did the exponential speed up of that algorithm by saying, well, I'm going to keep doubling and doubling and doubling until I can take no more and then start taking. So that's what we did last time. So Q and R exist. They are unique, and you have a means to compute them. So any question about this? Because we're going to use this heavily today. One last thing is that there's a hidden other symbol in here. So this is the existence symbol in math, corresponding to every existence symbol in a math theorem. I didn't write it, but there really is a this. So what is that? For all. So I need to tell you a math joke. So y'all are math folks. Y'all are math folks, and you'll end up meeting a lot of people who speak a different language than English. Maybe even you do speak a different language than English. But any math major can read this in any language and have a good laugh. Okay, so this is a theorem about math theorems. So, given a math theorem, for every in a math theorem, there is a there is. It's funny. Right? For all quantifier, there is a there exists quantifier. See, they come in pairs. Okay, fine.
You're a nerd.
Well, I've been called worse. Okay. Well, now you can go take this back and to the other math majors that aren't in here. You won't do it. Okay. Okay.
I'm gonna find you an example of a proof where there is a for all, but there's not if there exists.
Okay, good. Please do. I would love it if you did. Okay. So now this language is very useful, dividend, divisor, quotient, and remainder. But now we're going to venture into a new area where the language is used twice in two different ways. Okay, so you have to watch this part carefully. Okay. So remark. So this is the definition of a proper divisor. So let A and B be as above, and let Q and R also be as above. So if R is 0, right, because 0 is of the permissible values for R. If R is 0, then B is called a proper divisor of A. Okay, now for reasons historical and also for economy of language, it is also known as a factor. So factor and proper divisor are synonyms, and then this is all fine, and then here's the problem. It is also known as a divisor. Yeah. So now in this you say that B is the divisor in this procedure. Okay. Then you could say, for example, note that 20 is 4 times 5. So 4 is a proper divisor of 20. Okay. However, if you take 21 and divide by 4, it has quotient 5 and remainder 1. So 4 is not a proper divisor of 21, but it is the divisor in that procedure. Okay? So you could say 4 is a proper divisor of 20, 4 is a factor of 20, and you can also say 4 is a divisor of 20. So we were using divisor twice, once in the procedure of division, and then again to say that when you do divide by this, there is no remainder. We'll call it a divisor. Okay? So, if I could go back in history and modify the language, I would, but this is what we have. It's where we are. Okay. So, this is denoted as B tall bar A, and that is pronounced B divides A. Okay, so for example, to make the language clear, 4 divides 20. So this is true. 4 divides 21. This is false. Yes?
So, so I'm gonna just say that the tall bar is kind of like that was called like a little house when you divide like long ones,
Mm-hmm.
but like minus the square root on it. Minus the roof, like minus the chimney.
Right. This is a predicate. It either evaluates to true or false. So 4 divides 20 is true. 4 divides 21 is false.
And it's always and that's it.
Yes.
For that.
Yes.
Oh.
And then the way to negate the predicate is in this way. So 4 does not divide 21. So what about this?
True.
This is true. And 4 does not divide 20.
False.
That's false. Okay, so that's how we use that predicate. Good. So now, this is the set of divisors. So, div, so let a greater than or equal to 0, a in the integers, then div of a. This is the set of all divisors of a, is defined as the set of all b in the integers such that b is greater than 0 and, I don't want to use too many math symbols, so I'll just say and like this, and b divides a. Okay, so it's exactly what you imagine it to be. So, for example, the set of divisors of, say, 12. We want the set of all positive integers that divide 12. So what are they?
Question.
Yes?
So this is just like, depending on how, like, in like middle school, you do like this, like, you know what I'm saying? Like
Mhm.
1 times 12, 2 times 12.
Exactly this. Okay, so then what's the smallest divisor?
1,
1,
2,
2,
3,
3,
4,
4,
6,
uh-huh,
12.
12. Okay, good. So here's a disturbing one. Okay, so before we get to the disturbing one, how about the divisors of 13? 1 and 13. So such numbers that are like this, when the set of divisors of n is just 1 and n, that's so remarkable that we have a special name for such n. What are they called?
Prime.
Prime. Okay, good. That's not really relevant for today. Now, one thing that I want you to observe is given any integer whatsoever, given any integer, 1 is always a divisor. Right? So 1 is always a divisor. So 1, 2, 3. So now for all n that are greater than or equal to 0 and in the integers, 1 is in the set of divisors. So we never have to worry about this set of divisors being empty. It's always got something in it. In fact, 1 is always in it, and what else is always in it?
Itself.
N itself. Right, good. So now here's the disturbing one. Let's consider. What are the divisors of 0?
1 is 1.
0 is not,
Zero.
0 is not a divisor.
All real integers.
Well, 1 is in there, right? Because we just got finished saying that 1 divides everything. It's because because of the definition of division requires the divisor to be to be positive.
Okay.
So if you look on the first page, right, the divisor is b, and it's a requirement that b is positive. So in the end, that's the reason. The problem is that you could relax this. You could relax this, but then you give up uniqueness. So you have to have one or the other, right? Now,
Isn't it always E positive?
yes. So does 2 divide 0?
Yeah.
So what if you take 0 things and you divide them into groups of size 2? How many groups of size 2 can you divide 0 things into? 0 groups. And then how much remains when you do that? 0. Okay. Let's say if I give you 0 things and I want you to divide them into groups of 45. How many groups of 45 can you make from 0 objects? 0 groups. And then how much remains when you do that? 0. So what does it mean to be a proper divisor?
There's no remainder.
There's no remainder. So every time you divide 0 into any group size, there's always no remainder. So 1, 2, 3, ... which is to say the naturals. And I'll write a superscript plus just to make sure you understand that we're all in agreement, at least for this line, that the naturals don't include 0. So everything's a divisor of 0. In particular, that means that 2 is a divisor of 0, and in particular, that means that 0 is even. Okay, good.
That's the big question.
Yeah.
Very nice.
So now, this is the definition of common divisors. Let A and B be in the integers, A greater or equal to 0, B greater or equal to 0. Then the common divisors, C div, of A and B is the intersection of the divisors of A and B. So notably, because 1 is in that set and 1 is in that set, that means that 1 is in the intersection. So the set of common divisors is always non-empty because what is always in there? 1. So notably, 1 is in the set of common divisors. So yes, this is exactly what you think it is. So if I ask for, well, the divisors of 12, we wrote that up there already, so I'll just copy it. 1, 2, 3, 4, 5, 6. No, not 5, right? 6, 12. Gesundheit. The divisors of some other terrific number like 20. 1, 2, 4, 5, 10, and 20. So those are the divisors of 12 and the divisors of 20. So the common divisors of 12 and 20 are what? 1, 2, and 4. Any question about this? So what is the obvious thing that we're going to jump to now?
Least common factor.
Not that one, the other one.
Greatest common.
Greatest common divisor. Okay? So, greatest common divisor. Now, do understand that it's called greatest common divisor, okay, and we're going to call it that. But in your head, it might be helpful for you to parenthetically say greatest common proper divisor, okay, until you're fully comfortable with this language. So the greatest common divisor is So GCD, so I'll write it like this, GCD of A and B is the maximum of the common divisors of A and B. Now, every time you have a maximum, every time you write maximum in a math class, you need to be very concerned about the existence of such maxima. Okay? Because if the set of common divisors is empty, if it's empty, then this is not a well-defined function. So is the set of common divisors empty?
No.
No, it's not. Because on the previous page, we carefully said that 1 is always among the common divisors. Okay? So that means that this is well-defined. It's well-defined. Okay. So let's have an example. So we can use the stuff on the previous page. So how about the greatest common divisor of 12 and 20? So what is that?
4.
4. Right. Because if you look on the previous page, that is the set of common divisors, and of those elements, 4 is the greatest. Okay. Now, here's a disturbing one. Possibly. What is the greatest common divisor of 13 and 0?
13.
13.
Oh.
Because, do we all agree that the greatest divisor of 13 is 13?
Yes.
Okay. And then, now the question is well, is 13 a divisor of 0?
Yes.
It is. Because, what if I gave you 0 M&Ms and I said break them into groups of 13? How many groups could you make?
0.
0. And after you got finished making all those groups, how many would be left over?
0.
0. So, is 13 a divisor of 0?
Yes.
It is. So the greatest divisor of 13 is 13, and everything divides 0. So the greatest common divisor of 13 and 0 is 13. Okay, and this is symmetric, right? I could say, for example, what is the greatest common divisor of 0 and 13? 13, right? So in the end, the symmetry of the greatest common divisor, the symmetry of greatest common divisor comes from the symmetry of intersection. So if you look back to define the common divisors, we define it with intersection. Because intersection is symmetric, in the end, that means that the common divisor function is symmetric, and as a result, the greatest common divisor function is symmetric. Okay. So now we have, pardon me, the greatest common divisor of any number and 0, any non-zero number and 0. And now here is the last one that we need to know before we get to the general case. What about this, the greatest common divisor of 0 and 0?
Infinity.
So infinity is not a number.
It doesn't exist.
So yeah, this is not defined.
Oh.
This is not defined. Because what is the set of common divisors of 0 and 0?
C plus.
Yeah, it's the positive integers. And then what is the maximum integer? Infinity is not an integer.
The biggest number.
What's the maximum integer?
Oh,
Aleph null.
There isn't,
There isn't
which is not an integer, right? I agree that
Full value.
I agree it compares greater to all of them, but it's not an integer. So the fact that there is no maximum means that the greatest common divisor of 0 and 0 is not defined. So this is not defined. However, I have to put a big asterisk here. So mathematically, it's not defined. Mathematically, it's not defined. However, in all the programming languages that I surveyed over the past couple days, essentially all programming languages, if you type the greatest common divisor of 0 and 0, and you ask them to compute it, they'll give you a 0. So this is in, programming languages. However, it's just not mathematically correct. Okay. So now, here is the remark that will allow us to compute this greatest common divisor quite rapidly. So the way that you do it in grade school, more or less, is that you kind of try to list out all the factors of both numbers, and then you compare and say, oh, it's 4 or whatever. Okay, but that is not going to work for us because factoring integers is actually a quite difficult operation. It's quite difficult. So we want to be able to compute the greatest common divisor of a pair of integers without, in the first place, factoring both of them. So we want to avoid that. So we need this last observation. So suppose that we are given A and B in the integers. A is greater or equal to 0. B is greater or equal to 0. And one of them, at least, is positive. Which is to say, it's permissible that they're both positive or just one is positive, but I can't have that they're both 0. Now suppose in fact, I'll be specific and I'll say B is not 0. So B is the positive one. Suppose that A is B times Q plus R in the division. So we have Q and R. And suppose that D is in the common divisors. Of A and B. So that means that D divides A and D divides B, so it divides both of them. Okay? Then there exists M and N such that A is M times D and B is N times D. That's what it means to be a proper divisor. So D divides A, D divides B. And then we can take this equation. A is BQ plus R. And now I will replace A and B with MD and ND, respectively. MD equals ND. Q plus R. And now I'm going to solve for R. So solving for R yields MD minus NDQ. And I'd like for you to observe that on the right-hand side of this equation, is there a common factor? Of D, right? So that means that R is equal to M minus NQ D. Now what does that tell us about R? It is composite, unless D happens to be 1. But in particular, what does that tell us about the relationship between R and D? D divides R. Therefore, D divides R. Okay, well that's incredible. That's incredible, and that's incredibly useful because let's consider now. Consider B. Well, B is smaller than B is bigger than R, in fact, right? So what we're saying is that we want a common divisor of A and B, and to find a common divisor of A and B, it must also be a common divisor of the remainder, and the remainder is strictly smaller than B. Well, that means that we can iterate this procedure until it terminates in the following way. So taking those together gives us the definition of GCD, the computational definition of it. GCD of A and B is, so there are two base cases. One possibility is that the greatest common divisor will be A. So it's possible that the greatest common divisor would be A, and what is the base case where the greatest common divisor would be A? When B is what? When B is 0. So that's like 2 pages ago when we said that the greatest common divisor of 13 and 0 is 13. What's the other base case?
When A is equal to B? Or
Different one. So it'll be B when what? When A is 0. Okay, and now here's the case, the general case. So we can't have them both equal to 0 because we just got finished saying that that's not defined. So the last case is the case where neither is 0. So when I get here, I don't have to worry about either of them being 0. The answer will be that it is the GCD of B and R where A is BQ plus R. Now R has a name that we've used in class, so who can remember the name? We've used it actually in MATLAB also. Well, yes. So I'm being a little bit ambiguous. So R is A modulo B. Right. So this is a recursive definition. Why is this a recursive definition?
Because when you were finding the GCD of A, you're not finding the GCD of a different set of numbers.
This evaluation of the GCD depends on that evaluation of the GCD. So now, it's a good exercise, we're not going to do it, to prove that this must terminate. So, but the reason in the end that it's going to terminate is because R is smaller than B. Okay, by definition. R must be smaller than B. So if we recurse again, we'll recurse to another case where the new B, or where the new R is still smaller than the new B. And it will continue to recurse until we get to one of these base cases. Okay, that's the general idea, but we're just going to move on and do some computation now. So let's compute the GCD of, say, 32 and 60. So now, let's do it in our heads real quick, the same way that we did it in grade school. So, well, I can see that they're both even, so 2 works. Okay, I can see that they're both divisible by 4, right? So that'd be 32 is divisible by 4. That's 4 times 15, and then 15 doesn't have any more 2's in it, and this is all 2's. So 4 is the greatest common divisor. Okay, that's all working it in your head. Now let's ignore that entirely, and let's use the definition. Okay. So, GCD. So, when we enter this procedure, we have 32 and 60. So now, are we supposed to, yes?
Does that definition work where you're writing R is equal to A mod B? Like, does that work if, in either order, like if you put the bigger number on the left or on the right?
Let's watch. So in about 1 minute, I will have answered your question, not directly, only indirectly, and then I'll ask you again. Okay, so then are we presently at a base case? Which is to say, let me ask the question differently. What would it mean to be at a base case?
A or B equals 0.
Yeah, so it's equivalent to me asking, is one of these two numbers 0 currently? So no. So we must be in a recursive case. So now that means that the first argument we're calling A, the second B. What is the new first argument?
B.
B. So that means that this will be 60 now. Okay, and then what is the new second argument? The remainder when 32 is divided by 60. Okay, which is to say 32 modulo 60. So how many groups of 60 can you make from 32? 0 groups. And what remains when you do that?
32.
Now I claim I've answered your question. So what is the answer to your question?
Yeah, sure.
Well, so the answer is yes, but why is the answer yes? It'll still work.
Because the quotient is 0, so what?
Right. So let me see if I can paraphrase your question. It was, suppose that, so notice that there's 2 arguments. If they're different, then one of them's bigger, right? And to say your question, what if it's, I give you the smaller and then the bigger? Well, the very first recursive case will flip them. Okay? Now, are we in a base case?
No.
No. So that means that we need to recurse. What is going to be the new first argument? 32. And then what is the new second argument? It'll be 28, because now I'm giving you 60 things, and I'm saying break it into groups of size 32. How many groups can you take away from, how many groups of size 32 can you take from 60? 1. And then what remains when you do so? 28. Are we in a base case?
No.
No. So what is the new, that means we must recurse. So what is the new first argument?
28.
28. What is the new second argument? It'll be 4, right? Because now I've given you 32 M&Ms, and I'm saying make groups of size 28. How many groups of size 28 can you make? 1. And when you do so, how much is left over? 4. So the leftover goes here. Are we in a base case?
No.
No. So what is the new first argument? 4. Now I'm saying take 28 M&Ms and divide them into groups of size 4. How many groups can you make? 7. And how many are left over when you do so? 0. Are we in a base case?
Yes.
We are in a base case. Okay, which one are we in?
B equals 0.
Yeah, the second argument is 0. So what is the answer?
A.
the one that's not 0. Okay,
That's it, I think.
that's it.
With that, 32 is 6.
Okay, let's have another one. What time is it, by the way? I left my 24.
24.
Okay, so let's do another one, but let's construct it. So what do we want the greatest common divisor to be? We're going to work backwards. So what do we want it to be? 17. Okay, now I need two numbers that share no common divisors. Preferably, just any numbers, yeah?
31.
30, okay, 31 is another prime. But now I need one more number.
24.
Okay, 24 and 31 share no common divisors. So now I'm going to say that A is 17 times 31, 527, and B is 17 times 24, 408. Okay, now obviously, what is the greatest common divisor of A and B? 17. Okay, now we're going to forget that. GCD of 527 and 408. Okay. So we initialize the procedure with 527 and 408. And what is the first question we always ask?
Is A greater than B?
No, not that. Wait, so that's nowhere in the definition. Yes. Are we in a base case? No, we're not in a base case. So that means that we need to actually do something. So how many? We're dividing 527 M&Ms into groups of size 408. How many groups can we take away?
1.
1. And then what remains when we do that? Who knows, right? That's what calculators are for.
I feel like A is not equal 0.
119. So what's the new first argument?
408.
408. And I just did it carefully. A modulo B is 119. Okay, are we in a base case?
No.
Okay, we're not in a base case. So that means that we must recurse. So what is the new first argument?
119.
119. And the second one requires a little bit of computation. So now we have a group of size 408, and we want to take, no, sorry, we have 408 M&Ms, and we want to take away groups of size 119. How many groups can we take?
33.
3 groups.
What's left?
And then the question is, what's left?
17.
Is it 17? Okay.
That's fast.
Oh, this algorithm is quite fast. However, you have to remember that for every one of these rows, you're computing a long division. You're computing Q and R. Right? So then this is one of the reasons why you need a quick implementation, which is what we did last time, the exponential implementation of computing quotient and remainder. Okay, so then, is this a base case? No? Yes?
That should be 51.
Yeah.
Is it? Okay.
I didn't get 17. I got 15.
Okay. Okay, 51. Good. So, is this a base case?
No.
No. Okay. So then we have 119 M&Ms making groups of size 51. How many groups can we make?
2.
2. And when we do that, how many are left over? Okay, now we have 17. Okay, is this a base case?
No.
It is not. So the new first argument is 17. And the new second argument is, well, 51 M&Ms, groups of size 17. How many groups? 3. How many remain?
0.
0. And then we ask, is this a base case?
Yes.
It is. Therefore, the answer is whichever one isn't 0. 17. Right. Just like we designed it. Okay, any question about this? Okay, interesting. So this is greatest common divisor. This is the straightforward way to compute greatest common divisor. So any questions about this? Because now we're going to move on to something that has even more ness, greatest common divisor ness to it. This is okay? So now, here's the deal about greatest common divisor. There's a variety of instances in which it's useful. So in grade school, the only purpose of doing it in grade school is just to give children something to think about with arithmetic. That's it. Okay? You know, off the top of your head right now, you might be hard-pressed to imagine why are we interested in the greatest common divisor at all? Like, why is that even a thing? You can make good arguments about derivatives and integrals. Like, why are we doing that? Well, that's how engineering works. That's how we build bridges. But why would you want to compute greatest common divisor? Yeah?
I think the most important application is in banking encryption.
There's a good one. So modern cryptography uses stuff very similar to this. And what's necessary, in the end, one of the underlying things that's necessary for modern banking to work is you have to have two numbers whose greatest common divisor is 0. Oh, sorry, 1. Sorry. So you need them to have greatest common divisor of 1. So let's write that down real quick. For reasons that I can't make entirely clear, so given an A and B that are suitable for computation of greatest common divisor, so given these, when GCD of AB is equal to 1, that means that these numbers share no common divisors. So what does that mean about A and B? So this is called coprime. But don't be misled, because, for example, the GCD, so notably, the GCD of, say, 13 and 4, what is this? 1. And probably, when you look at this, the most outstanding reason to you that the GCD must be 1 is that 13 is prime. But don't be misled to think that a pair of coprime numbers, one of them or both of them, are prime. Because, for example, GCD of, say, 12, is 12 prime? No, it's actually pretty highly composite. 1, 2, 3, 4, 6, and 12. Okay, let's get another highly composite number. How about, no, 256 won't work because then we have a 2. How about 5 times 7 times the next prime, like that? So 385 is composite. Not, you know, it has 3 different factors.
And
Okay.
5 is 1 too.
Right.
It's still 1, right?
It's still 1, right? Neither one of those numbers is prime.
I'm not a big fan.
So encryption, in the end, the main component of encryption that makes it work is being able to find 2 numbers that are coprime. And the fact that factorizing integers is computationally difficult. Okay.
Or that it's more difficult. It's much easier to multiply it than to factor.
Yes.
Not reversible.
So, now another matter is that suppose that we have A and B, given A and B, and we've computed the greatest common divisor D. So we have 2 numbers. We've already computed the greatest common divisor. Then there exists, but not unique, there exists X and Y such that ax plus by is d, which is the GCD of a and b. And these x and y are in the integers. Which is to say that the greatest common divisor is an integer linear combination of the individual items. So, for example, 2 pages ago we established that the GCD of 32 and 60 is what? 4. So we did that last page or 2 pages ago. Okay, and what I want you to observe is that 4, can we think of numbers x and y such that 32x plus 60y is equal to 4?
That would be a negative number, right?
One of them can be. Can you think of 2 numbers that will do this for you?
2 for x, negative 1 for y.
Mm-hmm. X could be 2 and y could be negative 1. Okay. So now what we want to do is we want to be able to compute such an x and such a y. Okay? So here, it's a little bit, this one is, the problem is small enough that you could probably do it in your head. Two 32s and negative 1 60s will do it. To me, honestly, it's less clear, right? What are we going to need? I don't know. So we want to be able to compute it. How many 527s and how many 408s do we need to add together or subtract so that we get a 17? Okay. And we want to be able to do it quickly, right? So these numbers are called the Bezout coefficients. So there's a lovely bit of mathematics talking about the Bezout coefficients and how and why they must exist and everything else. We're just glossing over that because this is a programming class. Okay, but hopefully you'll take number theory or a course that has a bit of number theory and you'll see this. So what we want to do is we want to compute them. We want to compute them. Okay. So here's the general idea. Let's see if we can figure it out. Just reason our way to the end. So this is called the extended GCD. Extended GCD. And what it does is it computes not just the greatest common divisor, D, but it also computes x and y, the Bezout coefficients, and it does it at the same time. Okay, so given a suitable A and B, for which the GCD is a defined thing. The extended GCD, EGCD, of A and B, will still be recursive. And there'll still be base cases. So let's think about it for just a minute. One of the base cases is obvious. So there's 2 base cases. I'll write down one of them. One of the base cases should be A, 1, 0. Which is to say that the greatest common divisor is A, and that you'll need 1 A and 0 B's to get that. So A, 1, 0. And in what case should this be the answer?
Is it the same number?
When B is 0. Okay. Yes?
Is the extended GCD other than the
but I'm trying not to get too much jargon
Okay, my bad.
going. Okay, so what's the other base case?
E01.
B01. And this is the case when what? When A is 0. Which is to say, so what those two base cases mean, they mean that, suppose I ask you to compute the greatest common divisor of 13 and 0. Well, what is the greatest common divisor of 13 and 0? 13. And the way you could get 13 as an integer linear combination is you could take 1 13 and 0 zeros, and that'll give you 13. Okay, so now we have the base case, the recursive case. So we're surely going to have to recurse. And we're going to have to recurse to the same arguments that we did before, which is to say that we'll have to recurse to moving b to the first argument, and then what will be the second argument? Sorry? The remainder. Okay. So we'll have something. Wait. So the extended GCD, it will return for us a D, whatever the greatest common divisor happens to be, and we need to think about what's going to go in that position and what's going to go in that position. So let's think about it for a minute. So in doing this, in recursing, we'll have to recurse to EGCD of B and R. And A is BQ plus R. Is BQ plus R. Now, EGCD, this will have given us two values. It will have given us, say, an x1 and a y1. So by the time this recursive call returns, it will have given us a divisor and an x1 and a y1. For example, if we recurse to a base case, maybe this one is 1 and that is 0, if we happen to have recursed to a base case. So what this is telling us, that's telling us that D is AX1 plus BY1. AX1 plus BY. No, actually, that's not right. So let's fix this. What is this telling us? Because we recursed to B and R. So D is what? B x1 plus what?
RY1.
RY1. Okay? And now we have this R. We're going to substitute this R into that equation. I'm going to substitute it in there. So if we solve for R in this one, then R is what? A minus BQ. And now we're going to put this R in here. So D is BX1 plus A minus BQ Y1. So now what we need to do is we need to solve for the coefficients on A and B. So let's multiply this out and collect. So this would be BX1 plus AY1 minus BY1Q.
Why in that order?
Because I distribute it. Oh, why like that?
Yeah.
I don't know, you could have done it in the other order. Sorry. You like it in the other order?
Let's do it.
I write in graphite, it's never too late. Okay, so then now observe that B appears twice and A once. So this is AY1 and then plus B, and then what is the coefficient of B here? X1 minus, yeah, QY1. So that means that we recurse to this case, and then we are returned the greatest common divisor and those two Bézier coefficients. So the recursive case returned these two. We're going to return the same greatest common divisor because the greatest common divisor is not changed. But now we need to return new Bézier coefficients. What are the new Bézier coefficients? That one is the Bézier coefficient for A. And that one is the Bézier coefficient for B. Which is to say that this is all one big recursive case. So what we're going to return is D Y1 X1 minus Q Y1. So base case, recursive case. Interesting. So let's compute. So, yes?
I think I missed when you mentioned it. What was the E in GCD?
Extended. Yeah, which means that it computes at the same time as computing the greatest common divisor. It computes the Bézier coefficients. What time is it? 45. Okay, so I'll make a table of a computation of one of these in the homework, and then we'll do this on Thursday.
Wait, is this the extended GCD or the extended Euclidean algebra?
It's the same thing. So have a nice Tuesday.
You know what the culture in there does.
It's not a problem.
Alright, just making sure. Good day.